For steady incompressible flow in the z direction, the simplified equation of motion is 1 over r d dr r dvz dr, where vz is the velocity in the z direction, and that's equal to 1 over mu, which is the viscosity, dp dz, which is the pressure gradient in the z direction. So in this screencast, we'll show you how to find the velocity profile for flow through a pipe. We'll assume that this pressure gradient here is not a function of r or theta. As this is a second-order partial differential equation, we'll need to integrate it twice, resulting in two constants. So first, we multiply both sides by r. So that'll give us d dr r dvz dr equals 1 over mu dp dz times r. Let's integrate this. We get r dvz dr is equal to 1 over 2 mu dp dz times r squared plus a constant. Now we're going to divide through by r. Remember, we have to divide all of these through. So this is dvz dr is equal to now 1 over 2 times mu dp dz times r plus, don't forget this constant, that needs to be divided by r as well. And now we're going to integrate again, and we get that our vz of r, so our velocity in the z direction as a function of r, is equal to 1 over 4 mu dp dz times r squared plus c1 ln of r plus c2. So since there are two constants to solve for, we're going to need two boundary conditions. So let's look here. So we have this pipe, and we're going to say it has a radius here of r. So the first place we're going to look is at r equals 0. So if you look at our equation here and you put r equals 0 into it, notice what happens here. The natural log of 0 is infinity. And since the velocity cannot be infinity, we have to get rid of that term. So what we say is at r equals 0, our velocity is finite, and the only way that that can happen is that c1 has to equal 0. In other words, we have to get rid of that term. Okay, let's look at the second condition. So at r equals big R, which is the surface of the wall, the radius of the wall, the velocity is equal to 0. Again, that's because of no slip condition. So now what we're left with is 0 is equal to 1 over 4 mu dp dz times big R squared plus c2. And we can easily solve for c2, and we end up with a velocity profile, vz, is equal to 1 over 4 mu dp dz, little r squared, in other words, the variable r, minus big R squared, where r is that radius of the pipe. And so like pressure-driven flow between two parallel plates, the pressure-driven flow through a pipe, its velocity profile is parabolic.